G'day, Richard Marr here again from Mars Classes. I'm going to look at blackbody radiation today and try and give an explanation of it without too much hand-waving and try and explain it a bit more clearly than your textbook may be doing so. So first up, we'll just go through the standard definitions of what a blackbody radiator is. Essentially, it's an ideal thing. It doesn't really exist. It's something which will absorb all radiation that falls incident on it without reflecting it, and then will re-emit that radiation. A white body radiator is the exact opposite. That's something that reflects everything that falls on it. So this property of a black body radiator, if it did exist, would be something that all wavelengths and all angles of incidence of light are going to be absorbed and then re-emitted. So it's an ideal absorber of incident radiation. Another thing with that property is that it means it doesn't matter what the blackbody radiator is made from, what material it's made from, it will always give the same frequency of light will be emitted if the temperature is the same. So if it was made of one particular metal or another particular metal or clay or something like that, if the temperature is a particular temperature, it will emit light of a particular frequency. So why is this a big issue, the blackbody radiators? It's because there's something called the ultraviolet catastrophe. Around 1900, a couple of scientists, Rayleigh and Jeans, were trying to look at blackbody radiators and trying to work out what was going on in them. And so they were looking at it as in a classical sort of a system. They were looking at the classical physical arguments and some facts that they observed. And classically, it was thought that how the blackbody radiator operated was that there were, when heat was applied to the radiator, there was atoms, which are essentially charged particles, will be increasing their kinetic energy and will be vibrating. And as they oscillate, as we know, these charged particles, when they oscillate, will create a changing electric field, which creates a changing magnetic field, which will then give out electromagnetic radiation in the form of waves. And these waves, once they are emitted from the surface of the blackbody radiator, and the diagram I've got here is a cavity, you will get standing waves set up within that cavity. And because of the size of the cavity, you'll get different modes of vibration. The fundamental mode will be half a wavelength for the width of the cavity and so on. You'll notice that with the classical model, they thought that all these modes could exist, and they were all equally likely to exist within that cavity. So if you look at it, you can see that the shorter wavelengths, there's going to be a lot more of those shorter wavelengths in there. So looking at this classical model, it seemed to be that there's be a huge number of modes with the very low wavelength, and therefore there'd be huge amounts of radiation at those shorter wavelengths. So that's what the theory was saying. The theory was saying that at a higher temperature, you have higher frequency vibrations, which means a higher frequency of the electromagnetic radiation, which therefore means that you're going to be getting shorter wavelengths and a lot more shorter wavelengths, and a lot more of these short wavelengths will fit within the cavity. That's what the theory was saying. It also said as the temperature increased, the total energy of that cavity would increase as well, which makes sense. You're putting more energy in, the total energy would increase. And if it does increase, well, therefore the energy associated with those short wavelengths would also increase, but it actually increased to the point of infinity, which is mad, because that would mean that even a standard electric heater would be emitting dangerous amounts of X-rays and gamma rays. So that's what that ultraviolet catastrophe is about. The ultraviolet wavelengths and gamma down at those shorter wavelengths, they would just increase to infinity as the wavelength kept decreasing. So that's not what the observations said, though. Luckily, that's not what the observations told us, because if they did, as I said, any blackbody radiator would just be emitting stacks of X-rays and gamma rays and ultraviolet. So something was really wrong, and that's why they call it the ultraviolet catastrophe. The actual observations fit more like this purple line that I've drawn on the graph. So where have you seen a distribution curve like that before? That sort of shape there is very similar to when you graph the number of particles at specific speeds in an ideal gas. So could it be that, because these are particles in an ideal gas, could it be that these observations are matched to not waves but to particles? Well, it looks like that could be the case, and Planck thought so too. So he proposed that rather than the classical view that had the radiation being emitted continuously in waves, he said, well, it's probably being emitted in chunks or quanta. And his proposal was that each chunk can only be produced by one mode of vibration. And knowing that E equals HF, he knew that the wavelengths, the shorter wavelengths, would need more energy because E equals hc on wavelength, so it's inversely proportional. So he predicted, and look, there's complicated maths, we're not going to worry about that, but he predicted that the intensity of the radiation emitted by the black body increases to a peak when you get to a certain frequency, as like classical said, but then it drops back down, heading towards zero as you keep increasing the frequency or decreasing the wavelength. So Planck's concept of quantization of energy fit the observations perfectly. And what it ended up doing was changing our whole view of the universe, really. Because the image I've got here is showing that we can look at stars and we can look at the colour of the star, and from the colour of that star we can have some idea of the temperature of that star. Really quite impressive stuff, because as you can see, the peak keeps moving with the wavelength. So he gave a distribution that peaks at a certain wavelength and that shifts to shorter wavelengths for higher temperatures. And the area under the curve increases too as the temperature increases. So the upshot of all of this is, let's compare the two viewpoints. Let's compare the classical to the quantum viewpoint. And if we look at them, the classical theory had that graph that went up to infinity in the shorter wavelengths. The classical one was pretty reasonable at long wavelengths, but short wavelengths, there's a huge disagreement. So the Rayleigh-Jeans classical model said that as the wavelength decreases, the intensity increases to infinity. But the Planck quantum type theory had that when you got to that very short wavelength, that the intensity actually dropped to zero, and that's what we observed. Another thing is that as the temperature increases, the peak wavelength decreases, and this is the Planck quantum theory, and that's exactly what we observe as well. And the other thing that matches observations is that as the temperature increases, the total energy emitted increases. So that is, the area under the curve increases. So the Planck model, or the particle model, or the quantum model, fits all the observations. Now this is perfect science. You make predictions, you make observations, and then you explain. And this is exactly what Planck has done. I mean, with Rayleigh-Jeans and other guys, they had their theories, but it didn't match the observations. So we had to go away, look for a better explanation, and that's what Planck has done for us.